Hello, and welcome to Astronomy 100. In our previous segment, we were talking about the definition of temperature and talking about how scientists are able to quantify it, which means to attach a number to temperature. If you recall, the important definition is temperature is a measure of the average velocity of atoms or molecules that make up a particular substance. So when we measure temperature, we're measuring in reality the movement of atoms and molecules. Now, if you recall from the previous segment, to quantify it or attach a number to temperature, what we have to do is relate that temperature, relate the movement to something related to water. And what we talked about is how the phase change from solid to liquid or liquid to gas, these phase changes are when water goes from solid to liquid or liquid to gas. And the problem that we have, of course, is around the world there are two competing temperature scales. There is the metric system where we have centigrade, and in the United States we use Fahrenheit. And of course the problem is we have to convert between the two to be able to understand each version of temperature measurement. So what we do in most of the sciences, astronomy and physics and chemistry and sometimes biology, is we don't use the Fahrenheit scale, nor do we use the centigrade scale. What we actually do is we use what is called the absolute scale. And the absolute scale is one that was really a part of the work that was done by a man by the name of William Thomson. William Thomson was a scientist who worked in the area of understanding temperature around the end of the 19th century. And he was a Scottish man, and because he held a British title, his British title was Lord Kelvin. And what we do is when we talk about temperature on the absolute scale, we name the unit of increment or the unit of measure after Lord Kelvin, and the unit is called the Kelvin. And so on the absolute scale, we measure temperatures in kelvins, and we use the symbol K. You'll notice there is no degree symbol to go with that. Now, how is the absolute scale different? Well, the absolute scale is based on the actual concept of temperature. It's not related to water or any particular substance. It's based on this theoretical limit to what temperature could possibly be. To understand this, I want to show you a video that we took. Again, this is something that we saw in a previous segment. If you recall, we have this box with a bunch of atoms, and the atoms are going to move around based on their temperature. And what we're going to do is, you'll notice that when I play the video, there's a particular temperature that you see, and you can see that the atoms are moving around based on that temperature. But if we lower temperature, we slow down the movement of the atoms. So the idea is, what if we lowered temperature to the point where movement becomes less and less and less, but what if we go all the way to the point where all the movement stops? So what we're looking at is the idea of what happens when we go so slow, so low in temperature, that the meaning of temperature suddenly is meaningless. The idea becomes meaningless. So absolute zero, or the absolute scale, is the very, very lowest temperature you could ever get to where you take away all movement. It's essentially the temperature you get to where the concept of temperature loses its meaning. And so on the absolute scale, what we do is we base all temperature on this concept. And so by definition, absolute zero, otherwise known as 0 kelvins, is the point where all movement stops and the concept of temperature now becomes meaningless. So if we make that the 0 point on this scale, then you'll notice that there can never be a negative number, and all temperature is now related to this very, very bottom end of this theoretical limit, if you will, of what temperature can possibly mean. Now, to put this into practice, what we need to do now is relate the concept of temperature to what you see. If you remember, our goal is how can we determine the temperature of an object that is at some distance where we can't touch it, but we want the ability to see the light that comes from the object and determine the temperature of the object based on its light. To show you how this works, we have to go back to the year 1879, where a scientist by the name of Joseph Stephan was able to relate the concept of temperature to the light that you see coming from an object. To demonstrate this, what I'm going to do is show you a couple of pictures that you can see. We'll start with on the bottom of the screen here. What you're looking at is a piece of metal. This is a metal that a blacksmith has turned into this looped end, somebody who works in a blacksmith shop, probably in his barn. And he took a picture of the piece of metal, and this piece of metal is sitting on the floor of his barn. And the reason why we see the piece of metal is because there is sunlight or some sort of ambient light that is reflecting off of the metal, and of course we can see it. You'll notice it looks very dark, very black in appearance. Now, in reality, this piece of metal has a temperature. The temperature of this metal is room temperature. If you were to put your fingers on this metal, it would be fairly cool to the touch. But what we know is that if we put this piece of metal in a fire and got the metal hotter and hotter and hotter, what would happen is the metal would start to glow. And the color you always see first is the color red. And you probably are familiar with the term red hot. So the piece of metal that's been put in the fire becomes hotter and now starts to glow with the color red. If we take the piece of metal, put it back in the fire, and get the fire hotter and hotter, making the metal hotter and hotter, of course what you'll see is that the color to the metal will change, and it will actually start to look white. And you might even be familiar with the term white hot. So the white is simply the result of the temperature of the metal becoming hotter. Now the confusing part is white is not one of the colors of the rainbow, but we'll come back to that in just a minute. If we could put this piece of metal back in the fire again and stoke the fire even hotter, making the metal even hotter still, the color of the metal would then turn blue. So the hottest piece of metal would be blue. The cooler temperature of the metal, if it's at a cooler temperature, would be red. So notice the progression: red hot, white hot, and then blue hot. And so that progression of colors is not just a random set of colors. There's a reason for this. There's a meaning to why we see red first, and then as the temperature increases, we see blue last. Now, Stephan is able to tell us why this is by devising a formula. Let me show that to you here. The formula that you see on the screen is called Stephan's law. And what it relates is energy and temperature. This little symbol that you see right here means proportional. And the idea is energy is proportional to the temperature to the fourth power. So let me help you understand this a little better. Let's put some notes on the screen here. The E stands for the energy that is carried by the photons that are coming off of this piece of metal. So an example is down here. The metal looks blue because there are photons with the energy that is associated with blue coming from this piece of metal. So we'll just say blue photons are coming from the metal. So E is the energy of the blue photons. T is the temperature of the object that is emitting the photons or emitting the light. So T is the temperature of the piece of metal. E is the energy of the photons coming from this piece of metal. So what Stephan's law tells us is that if T becomes larger, then E also has to become larger. This is what we call a direct proportionality. If T becomes smaller, then E also has to become smaller. The 4 simply means that it's not a one-to-one relationship. If I make the T twice as big, the E is not twice as big because twice to the fourth power is actually 16. So doubling the temperature makes the energy 16 times higher, or lowering the temperature by cutting in half makes it 16 times lower. In reality, if you don't quite understand the 4, that's okay. The important part is the direct relationship between E and T. So here's the idea. When the piece of metal is first put in the fire, the temperature of the metal is low, and if T is low, E is low. And if you remember, when it comes to colors, red is the lowest energy photon on the visible spectrum. So the first color you have to see is red. But once the piece of metal becomes hotter and hotter, the T becomes larger, and therefore the E has to become larger. So eventually the metal starts to take on a whitish appearance, but as the temperature becomes very, very high, then the E has to become very large. And if you recall, blue is the highest energy photons on the visible spectrum. So the highest temperature is going to correspond with blue, and the lower temperature is going to correspond to red. And this is the reason why this piece of metal, or any piece of metal that you might experience, is going to first turn red and then eventually reach a whitish appearance, and if it gets hot enough, turns blue. Now, the important thing to understand here is what Stefan now discovers is that the temperature of an object is revealed by the light that the object gives off. You'll notice that I don't even need to touch this piece of metal to know that it's very hot. The color that comes from it, the light that comes from it, is telling me the temperature of it. So our goal is to find a way to know the temperature of an object by the light that it emits, and Stefan's law does that. It will tell us the temperature of an object based on the light that it emits that we're able to see. So this very important discovery is the link between electromagnetic radiation, or light, and temperature. And so now we have the ability to know the temperature of anything in our universe, not by physically touching it, by simply looking at the light that it emits, and then we have the ability to take the light that we see and figure out the temperature based on the light that we see. So this is an important breakthrough. To be able to turn this into a workable formula where we can now actually quantify the temperature of the object based on the light that we see, we still have a little bit more work to do. And in the next segment, we'll talk about how we're able to turn this into something that is in a workable form. And to do that, we have to understand the idea of black body. But we'll get to that next time. I hope you'll join me.